Hello students, I'm Babita and today we will have a small discussion on FET. What is this FET? FET is the acronym for Field Effect Transistor. As you can see in the picture, the component is shown here. It has three terminals. If you remember, even last year when you studied BJT, BJT was also a variety of transistor. BJT stands for bipolar junction transistor. And that component had three terminals, namely emitter, base, and collector. Similarly here, FET is also a variety of transistor and this also has three terminals. They are named as drain, source, and gate. Now let's know a little bit more in detail about this particular component. Of course, we all know that most of all these components, whatever we study, they are usually made up of semiconductor material. Similarly, this particular FET is also a component that is made up of semiconductor. Now, the last year component, that is the BJT, whatever you had studied, in that the word or the alphabet B stands for bipolar. Bipolar means it was a hint that was given to you through the name that the current conduction in this particular component happens because of both the polarities or because of both the positively charged holes and the negatively charged electrons. That means both the polarities are responsible for current conduction. Whereas here, this FET component, it is told to be a unipolar component. Now, what do you mean by this unipolar? Means in FET, the current conduction happens either because of holes alone or because of electrons alone. That means at a time only one type of polarity is responsible for current conduction. Hence the name unipolar. Now, if we have to define this component, it is defined as a three-terminal unipolar semiconductor device. In case of BJT's students, last year I had told you that there is a very important equation of BJT. We also used it several times in the class, that was IC is equal to beta times IB, wherein IC was the output current, that is the collector current, and the input current was the base current, that is IB. Now here the output current, it was controlled, that is IC was controlled through IB. Whereas in FET, the output current, it is controlled by the electric field that is applied across the conducting region. So here, since the electric field controls the output current of the component, we call it as field effect transistor. Field nothing but relates to the electric field here. Okay. Now, let us just look into the classification of FET. FET is basically classified into three basic groups. First one, JFET. JFET stands for Junction Field Effect Transistor. Second one is MOSFET, that stands for Metal Oxide Semiconductor Field Effect Transistor. And the third classification is IGFET, that is Insulated Gate Field Effect Transistor. Now, if we have to look into the further classifications of JFET, it is classified into N channel and P channel. Now, what this N and P channel are, we will study about that as we go ahead in the topic. Moving to the classification of MOSFET, it is classified into enhancement type and depletion type. Further, both are classified into N channel and P channel. Okay, so this is the basic classification chart of FET. Moving on next to the construction of JFET. Now here we are discussing the construction of N-channel JFET. As I told you, we will study about what the channel means at a later stage. See here, in this particular diagram, what you can see, the purple colored complete region, it is actually the N-type semiconductor. Actually, we call this entire rectangular shape as the bar of N-type semiconductor material. Now, in this N-type semiconductor material, On either sides, you can see the green colored region that is marked. This is nothing but the opposite kind of impurities. That means now here we have taken the drain to be of N type. So the opposite here will be the P type. So what we do is, in this N-type semiconductor bar, on either sides, almost in the middle of the bar, we will diffuse the opposite kind of impurities, forming the P-type semiconductor region here as well as here. These two together, a common terminal is connected like this, and from them a common gate terminal is pulled out. And if you look into this N-type bar, here at the upper terminal or upper end, we have marked it as drain, and a terminal connected to it, we call it as drain terminal. Similarly, at the lower end, we have another terminal connected, which we call as the source terminal. So the three terminals of this particular component, that is FET, are drain, source and gate. Now in the N channel, the bar is of N-type material. That is why you call this as N-channel FET. Alternatively, if we talk about P channel, that time this entire whatever the bar we have taken, it will be of P-type material, and whatever this P-type material you see here, that will be of N-type material. That means it is just the opposite. In case of P channel, since this complete channel, this channel will be of P-type material, hence you call it as P channel FET. But here students, we are discussing about N-channel FET construction, and that is why I have taken this channel to be of N-type material, and this diffusion is of P-type material, which forms the gate. Now the space between these two P-type diffusion areas, what you see, that we call it as the channel. Here I have shown the circuit symbol representation for both N channel and P channel. If you see, the circuit symbol for both are almost the same. The only difference is in the type of arrow or the direction of the arrow that we discuss about. In case of N channel FET, you can see that the arrow is pointing towards the particular component, whereas in P channel, the arrow is pointing away from the particular component. So if the arrow is pointing towards the particular component, we call it as N-channel JFET, and if the arrow is away from the component, we call it as P-channel JFET. Students, now we will start with the operation of FET, that is, we will see how the FET operates. In the normal operation mode, what happens is, the gate is reverse biased with respect to source. Now in the circuit diagram, what is shown here, you can see that VDD, it is the biasing supply applied between the drain and the source here. And VGG, this is another biasing supply that we are using here, applied between the gate and the source. Okay. Now VDS, it is the voltage that is developed because of VDD between the drain and the source terminal. That is why it is named as VDS. That is voltage across the drain and the source terminal. Similarly here, VGS, it is the voltage that is developed across the gate and the source terminal because of the applied voltage VGG. Okay, so VGS is nothing but the voltage that is developed between the gate and the source terminal. Now in the normal operation, what happens is, the gate is reverse biased with respect to source. Now you can see here the negative terminal of the battery is connected to the P-type gate, and the positive terminal, it is connected to the N-type source. Because of this, the PN junction here, it is reverse biased, and this whatever region you are seeing, it is nothing but the depletion region because of the reverse biasing of the PN junction. Also students, you can see that the depletion region here, it is shown to be much more wider. The reason for this we will discuss shortly. So as of now, what you are observing is the depletion region here, it is existing between the P and the N region because of this source voltage that we are applying. And because of this depletion region that is formed here, what happens is the gap available here for the electrons to flow is slowly getting narrowed. Okay, this gap we call it as the channel. Now the majority charge carriers enter from the source terminal, flow through this particular channel, and then go reach the drain terminal. This current, it is known as ID, that is drain current, represented as ID, and this current is controlled by the voltage that we apply here, that is the reverse passing voltage applied to the gate terminal. The P region is heavily doped when compared to the N region here. So this is the P region here and this is the N region. This P region is heavily doped when compared to the N region here. And because of this, what happens is the depletion layer penetrates deep in the N region and it penetrates lightly into the P region. I repeat, the depletion region penetrates deep into the N region, whereas in the P region, the depletion region does not penetrate that deep. The reason for this, I will explain it to you using the Paint app. So we'll just see how it happens. Here I have taken the help of Paint app to discuss how the depletion region penetrates deep inside. Now here I have taken a p-type semiconductor which is heavily doped. Of course I have shown the charge carriers only near the junction area. I haven't shown the charge carriers here in deep inside the p-type semiconductor region. Similarly this side I have taken the n-type semiconductor which is lightly doped, and here as well I have not shown the electrons deep inside the n-type region. Now this is the surface of junction. Okay, so now you have already studied last year that when the p-type semiconductor and the n-type semiconductor form the junction and there is no voltage applied across it, that time initially a depletion layer is formed near the junction. Okay, now say for example uh, in the depletion region, say just for example, okay, let me take that, say 10 holes from the p side recombine with the 10 electrons on the n side, and this recombination helps in formation of the depletion layer. Now as I've already told you, p-type is the heavily doped region. So if I want 10 majority charge carriers, that means 10 holes from the p side. If I travel very short distance from the junction area into the p region, I will get all those 10 holes here. So you can see that the amount of distance that I'm traveling from the junction deep into the p-type is very little. Let me just mark that here. So at max what I can tell is I have come so much deep inside the p region. Okay. Now similarly, if each of these 10 holes have to be recombined with the 10 electrons on the n-type region, that time what happens is to get those 10 electrons, since this is lightly doped, I have to travel much more deeper into the n-type region. So to get those 10 electrons to counterbalance these holes, you can see that I have to travel much more deeper. Say for example, if I have to mark it here, I can mark it as something till here. Okay, so now you can see the depth that have gone into the p-type region, and you can also see the depth that have gone into the n-type region. Though it is same 10 holes on this side and 10 electrons on this side, since p-type is heavily doped, I get those 10 electrons very much near to the junction surface. Whereas in the n-type, since it is lightly doped, to get the same 10 electrons, I have to travel much more deeper into the n-type. This is why when the depletion layer is formed such that one type of semiconductor is heavily doped and the other is lightly doped, that time the depletion layer penetrates deep into that side which is lightly doped, whereas on the heavily doped side the depletion layer does not travel that deep inside. Now, hoping that you have understood the penetration of a depletion layer, that why one side it penetrates deep inside whereas the other side it does not penetrate that very deep, we will proceed to the next level of explanation. Now we will explain the working of this particular FET in two levels. First one is when the VGS voltage is not applied. Okay, that means the VGS value here will be almost zero, and what we will do is the VDS will be increased from zero. So that means this voltage is not applied in the circuit, whereas this voltage will be applied. So because of this, what happens is as the gate is the gate voltage is not applied, the depletion region does not exist that much. Or I can just make small change in the circuit diagram, and now the diagram will be something as in the first diagram, this one. So here between the gate and the source there is no voltage that is applied, and there is only VDD that is applied. Because of this, what happens is the reverse biasing that would otherwise exist between the gate and the source junction in this region, students, this reverse biasing or the depletion region here is not there, and the result of that is you can see that the channel width is wider. Just compare it with diagram 2 here. Since the depletion region is present here, you can see that this blue color region, which is actually the channel through which the electrons will flow, or the holes, either ways. Here since we have taken N channel, so it will be the electrons that is flowing. So since here the channel is narrower because the depletion region is present here. Whereas the same thing, if you compare with this diagram, you can see that the depletion region is not present here, and because of that the channel width is wider. Okay, so now what happens is because of the voltage VDD applied, the drain is connected with the positive terminal and the source connected with the negative terminal. So the electrons will flow from the source terminal to the drain terminal, constituting the drain current. Now this drain current, it is given by the expression ID is equal to VDD by RDS. You all know that VDD is nothing but the biasing supply that we are using here, and this RDS, it is nothing but the resistance between the drain and the source terminal. That means whatever this channel is there, the resistance offered by this channel from the drain end to the source end, that is represented by RDS. Now since VDS reverse biases the drain with respect to gate and forward biases the source with respect to gate, the reverse biasing is less near the source end and is maximum at the drain end. Because of this, what happens is the channel becomes narrower at the drain end here, whereas at this end the channel will be much more wider. To understand this, students, I just want to use the paint application once again. Now here I have taken a simple diode and I have applied voltage across that diode such a way that the diode is forward biased. You can see that the positive side of the diode I have connected it to the positive terminal of the battery, and the negative side of the diode I have connected it to the negative terminal of the battery. Okay, now from this battery biasing, you can understand that the positive side of the diode is at a higher potential because I've connected the positive terminal of the battery, whereas the negative side of the diode, it is connected to the negative terminal of the battery. That means it is at a lower potential, and under this condition the diode is forward biased. Now what I do is I just make a simple change to the circuit. Just observe. I'm just taking out the battery representation. Instead, I will just represent this to be the positive side of the battery. And this one, I will represent it as the negative terminal of the battery. Now, say I apply voltages to both these ends. As I told you before, for this diode to remain forward biased, the potential on this side should be greater than the potential on this side. So say for example, I will apply a potential of say 5 volts this side, and here I will apply a potential anything that is less than 5 volt, say for example 3 volt. Okay, so now in this condition, I tell that the diode is forward biased. Okay, because the potential on the positive side is more than the potential on the negative side. Now, say I apply some other values, something like instead of 5 volts and 3 volts, I will apply, say here, say 2 volts. That time, what should be the voltage that I apply this side so that the diode is still forward biased? It should be any value that is less than 2 volts. Say I apply 0 volts. Okay, so now even now 2 volt is applied to the positive terminal, 0 volt is applied to the negative terminal. That means even now I say that the diode is forward biased. I'll just show you another value. Now what I will do is, instead of 2 and 0 volt, I will apply a different value. This side I will apply 0 volt. Now think and tell me what should be the voltage that I should apply on the negative terminal so that even now the diode is even now the diode is forward biased. As I told you, for the diode to remain forward biased, the requirement is the potential on the positive terminal should be greater than the potential on the negative terminal. So since I have applied 0 volt here, I should apply any value that is less than 0 volt this side. That means say minus 2 volts. Now I have applied 0 volt here. I have applied minus 2 volts here. That means the potential on the negative terminal is even now less when I compare it with the potential on the positive terminal, or the potential on the positive terminal is greater when I compare it with the negative terminal. So even now I tell that the diode is forward biased. Until the voltage at the positive terminal is greater when compared to the voltage at the negative terminal, the diode is always forward biased. Similarly, if I maintain the voltage at the positive terminal less than the voltage at the negative terminal, that time I can effectively reverse bias the diode. I repeat again, in this particular case, what you're seeing is the positive terminal is held at a higher potential when I compare with the potential at the negative terminal, irrespective of their values. Similarly, if I maintain the potential at the positive terminal less than the potential at the negative terminal, then irrespective of the values, the diode will always be reverse biased. That means if I have to reverse bias this particular diode now, considering this voltage to be 0 volt, I have to change this value to something, say plus 2 volts. Okay, I think it's visible now. So here what I've done is I've maintained the positive terminal at 0 volt and I have maintained the negative terminal at plus 2 volts. So now you can see that the potential at the negative terminal is greater than the potential at the positive terminal. So because of this, what happens is the diode is now reverse biased. Similarly, irrespective of the voltage values that I apply to the positive and the negative terminal, until and unless the potential at the negative terminal is greater than the potential at the positive terminal, always the diode is reverse biased. So now applying that logic here, we can see that the voltage VDS reverse biases the drain, that is N region, with the gate, that is P region, and because of that the depletion region here is shown so much. Now talking about the same voltage source, that is VDS, this voltage actually forward biases the source with respect to the gate, whereas VGS, it reverse biases the gate and the source junction. So that means the resultant effect will be observed at the source and gate junction. So because of that, what happens is there is some amount of forward biasing here and some amount of reverse biasing. The net effect of that is reduced reverse biasing here, because of which the depletion region shown here is little narrower when compared to the depletion region shown here. Okay, and this results in a wedge shaped form here. This shape of the depletion region, we call it as wedge shape. Because of this wedge shaping of the depletion region, what happens is the channel width will be narrow at the drain end, whereas it will be much wider in the source end. In the previous type of working, what we discussed is only VDS was applied and VGS was not applied. Now in this condition, what we do is we will keep VDS at a particular constant value and we also apply VGS. This VGS is nothing but the reverse biasing potential, and therefore we will decrease it from 0. That is, in the scale of, like, after 0 we go for -1, then -2, then -3, and so on and so forth. So now, as we keep on increasing this voltage, remember when I tell increase, I am telling it in the negative scale. So as we keep on increasing this VGS voltage, what happens is the reverse biasing here keeps on increasing. That means the depletion region keeps on widening. Now, as we further increase VGS, as we studied before, the same phenomena occurs again. The depletion region keeps on widening, and for a particular value, what happens is the depletion region would have reached its maximum. Okay, so as we are increasing this VGS, as the depletion region grows, as the channel width becomes narrower, the current flowing through this particular channel is given by this expression. That is, ID is the drain current, given as IDSS into 1 minus VGS by VP whole square. Here VGS is the gate to source voltage, VP is the pinch off voltage, IDSS is the drain to source saturation current. Now, as we further keep on increasing VGS, a particular value is reached wherein the depletion region would have reached its maximum. That means the channel width now would have reduced to its minimum. So minimum that the two depletion layers look like almost they are touching each other. But actually they are not touching. So that means the channel width is now like almost reduced to 0, but not exactly 0. Or in other words, the channel width is at its minimum. This particular value of VGS, for which the channel width is at its minimum, it is known as pinch off voltage. Remember, we defined pinch off voltage in two terms. First, we termed it, or we defined it in terms of VDS, and at that point of time we did not apply VGS in the circuit. That is one way of defining pinch off voltage. The other way of defining pinch off voltage is by applying VGS, keeping VDS constant, and then we tell pinch off voltage to be that value of VGS for which the channel is almost reached to a minimum width. Now, when the channel width is reached to its minimum, that means the current is also reached to its minimum. Since the channel width is almost like the width is 0, but not 0. So the current ID will also be like almost equal to 0, but it is not exactly equal to 0. It will be at its minimum possible value. Students, with this we come to end of the working of FET. The other topics on this particular chapter, I will cover it in the second video of mine, which will be shortly, the link of that will be given to you people. Thank you students. Have a good day.